Hello. So you can see that we have a new class today. It's a class of 1. Do math and you can do anything. Hopefully he will enjoy the class as much as you will. We are going to continue talking about probability. So we talked about classical probability and empirical probability. Now we're going to talk about probability of multiple events occurring together. So in order to do that, we need to talk a little bit about the different types of events that there are. So we're going to start with independent events. So for independent events, and we could talk about multiple events. I'm going to stick with 2 for right now, but this applies to if you have 3 events, 4 events, 10 events, 100 events. Okay? Independent events is when the outcome of one event does not affect the outcome of another. For the outcome of the first event does not affect the outcome of the second. So let's take some examples. Okay, so one example would be if you were tossing a coin, okay? If you were tossing a coin 2 times, if you were tossing a coin twice, then the outcome of the first would not affect the outcome of the second, meaning if you tossed a coin and you got a head, it doesn't affect what you're gonna get on the next, it doesn't affect what you're gonna get on the next toss. So tossing 2 coins, those are independent events. Let's take another one. So I think most of you know decks of cards pretty well. We will go through that in more detail here, trying to put this into the screen. So if we have 2 decks of cards and we pull a card from the first deck, okay, so we pull a card from the first deck and then we move that deck and we pull a card from the second deck, these are independent events. What we get on the first card of the first deck has no influence over what we get for the first card on the second deck. Both decks have 52 cards, so we haven't changed anything about the second deck by pulling out the first card. So again, we have 2 decks of cards. I put them on top of each other. This is what our bear likes to do in his spare time. Okay? So if I take a card out of that first deck, I've changed the first deck. But I haven't changed that second deck. That second deck is completely independent of the first. So if I pull a card from that second deck, it has no influence over what happened by what we did in the first deck. Okay? So these are independent events. Okay, so let's write that down. So just as examples. Tossing a coin twice. So if we get a head on the first toss, doesn't change. What we could get on the second toss. So that's one example. Second example would be pulling a card from one deck then pulling a card from a new deck of cards. It's important that we say a new deck. We could also say pulling two cards from the same deck, but after we pull the first card, we put it back before pulling the second one. Those would also be independent events. That's just another way of doing the same thing. The probability of getting ahead on the first toss is 1/2. The probability of getting ahead on the second toss is 1/2. A deck of cards has 52 cards. So the probability of getting any card on the first pull is 1 out of 52. Probability of getting that same card on the second pull is 1 out of 52. Okay? So these are examples of independent events. Then we have dependent events. So dependent events, not surprisingly, is the exact opposite. Again, we're going to specify for 2 events, but we can expand this to multiple events. So independent events would be the outcome of the first event does not affect the outcome of the second. The outcome of the third is not affected by the outcomes of any of the previous ones. And actually, I think I wrote this... This doesn't make sense the way I wrote it. It should be the outcome of the second effect of the second event. No, I did it right. Ignore me. Just ignore what I said. The outcome of the first event does not affect the outcome of the second. Sorry. So dependent events, it's saying the outcome of the first event does affect the outcome of the second. It could change the outcome of the second. For example, let's say We have a bag of M&Ms. And we're gonna say it's a small bag. So we're gonna say that there are 3 red, 6 blue, and 2 brown. And we take out 2 M&Ms. To eat. It's important to say that we're eating them because we're not replacing. We're not taking out an M&M and then putting it back. So this is dependent because if I take out a red, okay, then there's 1 less red. There's also 1 less M&M, okay? So in other words, the probability of getting a red in the beginning, well, there are 3 red and there are 11 M&Ms in total because 3 plus 6 plus 2 is 11. So the probability of getting a red on the first one is 3 out of 11. Now let's say that we chose a blue on the first one. Well, now the probability of getting a red is only 3 out of 10 because we have 1 less M&M, okay? The probability of, let's say instead that we chose a red. Well, now there are only 2 red, so it's 2, and again, it's out of 10, okay? So probability of getting a red on first take is 3 out of 10. If we got a blue, well, now the probability of getting a red on the second take, sorry, this is 3 out of 11. Okay. This is only 3 out of 10 now. Have 1 less M&M. So the 11 is the total number of M&Ms. Right? This is number of desired outcomes over the total outcomes. So the total outcomes comes from adding the 3 plus 6 plus 2. So we get 11. But we took an M&M out. We took out blue. So now we have 1 less M&M. So our total outcomes, instead of being 3 plus 6, it's only 3 plus 5. We have 1 less. So what we got on the first one changed the probability on the second. Let's change this. Let's say, and this will really show you why it's dependent. So here we got a blue first. Let's change this and say, suppose we got a red first. Then the probability of getting a red on the second take changes. Now the probability of getting a red is 2 out of 10. There are only 2 red M&Ms left. And there's 1 less M&M. So now there are only 10 M&Ms. So notice that what happened on the first changes the probability of what happens on the second. In this case, if we get a blue first, we get 3 out of 10. But if we get a red first, we only get 2 out of 10. So that's what makes something like this a dependent event, okay? Okay, so now that we know what independent and dependent events are, we can start calculating what independent and dependent is and what independent and dependent probabilities are. And we use something called conditional probability. We did this at the very beginning of the semester. If you go back, I think we did it on the very first day actually, and we were talking about the probability that if you go in for a mammogram and you get a positive test, what's the probability that you actually have breast cancer? So if you go back way to the beginning, if you remember, we said there's only a 10% chance that you actually have cancer. If you're at the age of 40, there's only a 10% chance that you have cancer if you test positive, if your mammogram is positive, okay? That's conditional probability. Conditional probability is what is the probability of one event occurring given that another event already occurred. So let's write that down. So conditional probability. Notice we're talking about two events, and now we're using whether they're dependent or independent to calculate conditional probabilities. Conditional probability is the probability of an event occurring that another event already occurred. And the way that we write this is probability of A given B. This is the probability of A given that event B already happened. So we actually did this just now. When we were taking this example, we said, what's the probability of getting a red on the second take, given that we got a blue on the first? This is the probability of getting a red on the second take, given the probability that we get a red on the first. So I'm just going to write that in here. Just as an example. So in the example of independent events, sorry, not independent, dependent. We said the probability of getting a red on the second, given the fact that we got a blue on the first. And that was 3 out of 10. And then the probability of getting a red on the second, given the fact that we got a red on the first. And that was a 2 out of 10. So this is conditional probability, okay? So what I'm going to do is in some of the in the rest of this lesson, I'm going to use lots of different examples, but some of them are going to be using decks of cards. It's a great example of probability because there are so many different aspects of a deck of cards. So I just want to go through and write down some of the different aspects of a deck of cards. I realize a lot of you already know this, but there are a lot of people who don't know. So this is just a side note. I'm going to put this in brown. It's just a side note. So these are just the different aspects of a deck of cards. There are 52 cards. Okay. There are 13 red and 13 blue. I'm sorry, 26 red and 26 blue. I hope I'm not confusing you too much. 26 red and 26 black. I don't know where my head is. 26 red and 26 black. Okay? Of these 26 red, 13 are hearts. That's the suit of the card. 13 are diamonds. I'm going to move this 26 black over. So we have 4 suits. 13 of these are clubs, and 13 13 are clubs, and 13 are spades. And I'll show this to you in the camera so that you can see. Okay? Now, of each of these suits, okay, the 13 cards. So these are suits. That's what we call them. Okay? So we have 4 suits. Hearts, diamonds, clubs, and spades. These are our 4 suits. Okay? There are 13 of each. The hearts and the diamonds are red, and the clubs and the spades are black. And then in each suit, we have an ace, and then there are number cards, 1, 2, 3, 4, 5, 6. There is no 1. The ace is like the 1. It's been a long day. We have an ace, a 2, a 3, a 4, a 5, 6, 7, 8, 9, 10, and then we have what we call a jack, a queen, and a king. And these are referred to as face cards. Okay, and that's because they have faces on them. So there are 4 aces, 1 heart, 1 diamond, 1 club, and 1 spade. That's true for all of these. There are 4 twos, 1 of each suit. There are 4 jacks, 1 of each suit. Okay, so that's what gives us the total of 52. So for example, this is a 7 of spades. So you can see the shape. The shape is what tells you the suit. This is black, and then you see the number. Okay, let's switch this to full camera. Okay, so this is a 7 of spades. By contrast, this is an ace of diamonds. Okay, so you can see the diamonds. Ace is like a 1, so you only see 1 diamond. This one is a jack of spades, so that's why it's called a face card, because the jack has a face on it. It's spades, you can see the shape, so we call it a jack. Sorry, just going through the deck. This is what the hearts look like. 3 of hearts, you can see it's just a heart. This would be like a 10 of clubs. This is the queen, so queen of diamonds. So you can see that the shape is the suit, okay? And the king, queen, and jack, so here's a king. This is a king of clubs. So that shape is a club. And you can see jack, queen, king are all face cards. And then again, the shape that you see on the card is the suit. And the clubs and the spades are black, and the diamonds and the hearts are red. Okay, so that's what a deck of cards looks like. So we're gonna use that. Okay, so sometimes we'll use cards, sometimes we won't, but I just want you to be familiar with it. So let's go back to probabilities. So let's say, what is the probability of getting a queen? So we're just going to choose one card first, just so that you get familiar with probabilities. Okay, probability of getting a queen, well, there are 4 queens, and there are 52 cards. The probability of getting a red card, well, here, there are 26 red, and there are 52 cards. And you should make a habit of reducing. So 4 out of 52 can reduce to 1 out of 13. 26 out of 52 reduces to 1/2. Okay. The probability of getting a diamond, hang on, I'm pausing this. Okay, so the probability of getting a diamond here, there are 13 diamonds and 52 cards, and that's 1 out of 4. So you can get the idea as to what the probability of 1 card is. Let's take 2 events, okay? So we're going to do the probability of a queen given the fact that we got a king. Okay, so now we're selecting 2 cards. Well, we already chose a king, and because we already chose a king, there's 1 less card. Only 51 cards. King is already taken away. Now we chose a king, which means that we still have all 4 queens. Okay, so let's just make sure that that's clear to everybody. We still have all 4 queens. We know that because we chose the king. But we have 1 less card. Let's say the probability of a king, given that we chose a king. And for this is 3 out of 51. We have one less king. So not only do we have one less card, but we have one less king. So the difference is when we chose a queen on the second card, we still had all of our queens because we chose the king. Okay, let's look at another example. Let's take a table, okay? So we're gonna go to empirical probability, okay? So suppose we ask the students if they have ever been offended by something on social media. The following responses, and we're going to break up these responses in terms of male and female, okay? So we're breaking them up. So we have our yeses, and we have our nos, and we have female, we have male, and we're going to put in totals. So the number of females who said yes were 619. 619 females said yes. 649 said no. And if we add that together, we get a total of 1,168 females. Okay? Now for the males, 532 said yes, 576 said no, which means that there were 1,108 males in total. Now we can add these columns, okay? So the total number of people who said yes, male or female, was 1,151. Let's actually put these in different colors so that you can see them as totals, okay? So that you can differentiate. So 1,168 were females. That was the number of females asked. 1,108 males were asked. And the total number of people who said yes, we just add it together. 1,151 people said yes. 1,125 people said no. And what that means is that 2,276 were asked. This is the total who said yes. Total number of females. Again, it's been a long day. I don't know why I keep saying the wrong thing. Total females. Okay, so we're going with the column, with the row. Total females. This is the total males. This is the total number of people asked. This is the number of people who said yes. This is the total number of people who said no. And again, total number of people asked. So this 2276 is if we added these two numbers together or if we added these two numbers together. 532 is the number of males who said yes. 619, the number of females who said yes. Okay, so this is the two events happening at the same time. So let's do some probabilities here. So let's just take some probabilities of single events. So we're not talking about conditional probabilities. We're saying, what is the probability that the person who we're talking about is a female? So in other words, we're pulling one person who we asked, and we're saying, we're putting all 2276 people in a room, okay? All 2,276 people we're putting in a room, and we're pulling out one of them. And we're saying, what's the probability that that person is a female, okay? So the total number of females is 1168. That's the desired outcomes. And the number of people in that room is 2276. By contrast, the probability of people that the person who we pull out said yes. Well, the number of people who said yes is 1151. That's the desired outcomes. The total number of people, 2276. Okay, so let's do a conditional probability. Let's say that we want to know the probability that somebody is female given the fact that they said yes. So we already know that we're only choosing from the yes people. So instead of choosing from the whole group, we're only choosing from the people who said yes. We already know that the person said yes. So think about it this way. We're putting all the people who said yes in a room by themselves. There are 1,151 people who said yes. 619 of them are female. So this is going to be 619 over 1,151. 619 females, that's the desired. So females who said yes, we're only looking at those females. All the yes people are going into a room by themselves, okay? And then we're saying, okay, well, we're choosing one of those people. What's the probability that they're female? Well, the yes people, that's 1,151 people in that room. 619 of them are female. Let's say that we want the probability of a yes, given that somebody is male. So now we're changing it. We're taking all of the males and we're putting them in a room by themselves. So we're taking 1,108 people, we're putting them in a room, and we want to know what's the probability that that person or that man said yes. Well, now there are 532 men who said yes, and there are a total of 1,102. Okay, so this is like the probability of the people who said yes and are male over just the number of males who said yes over all of the males. Okay, this one, it's the probability of female, it's the number of females who said yes over the number of people who said yes. So what goes in the bottom, what goes in the denominator is just the number of yeses in total. And what goes in the numerator is the number of females who said yes. Okay? Okay. So let's see what this has to do with dependent and independent events. So two events are independent if the probability of B given A is the same as the probability of B. In other words, we're saying the fact that A happened is irrelevant, okay? And that kind of makes sense. We're saying that if B happens, that the outcome of the first doesn't affect the outcome of the second. So it makes sense to say, hey, it doesn't matter if we chose A or not. The probability of B is always going to be the same. Okay? So, and vice versa. The probability of A given B is just the probability of A. Okay, so let's just check one of these. Okay, we can do one of these. We can say, is the probability of being female given yes, given answering yes, the same thing as just the probability of a female? So we know what the probability of being of a female given a yes, that's 619 over 1151. And we're asking, is that the same thing as just the probability of female, which is 1168 over 2276. And if we go to our calculator and we calculate each of those, 619 divided by 1151 is about 0.54. And 1168 divided by 2276 is 0.51. It's not the same. Let's do the same thing with a probability of males, okay, of the yes given the male. And we're saying, is this, I'm covering the screen, is this the same thing as just the probability of saying yes? So we calculated earlier that probability of yes given a male is 532 over 1102, and the probability of saying yes is 1151 over 2276. And we're asking ourselves, are these equal? If they're equal, then they're independent events. So we could go to our calculator again. 532 divided by 1102 is not, that's not right. I knew that that was incorrect because I got a number greater than 1, and probabilities are always less than 1. So this is 0.48, and we're asking ourselves, is it the same as 1151 divided by 2276? And we get 0.51. It's close, but it's not the same. It has to be the same. So this is not equal, and this is not equal, okay? These are dependent events. One affects the other. They're dependent. Okay, dependent events because this is not true. Okay. So this is just an example. If we talk about tossing a coin, the probability of getting a head given a tail on the first toss. So this is tossing a coin twice. This is 1/2. And the probability of getting a head by itself is just 1/2. So these are independent events. They're the same. Okay, so let's take another case, okay? So something else about calculating probabilities. So when we calculate probabilities, we can use these things to help us determine if events are dependent or independent, okay? So if events then the probability of A and B happening together is the probability of A times the probability of B given A. And we'll go over this in 1 second. Okay? If two events are independent, then in this case, the probability of A and B happening together is just the probability of A times the probability of B. Now think about this for a second. It makes perfect sense. We're saying that if two events are independent, then the probability of B given A is equal to the probability of B. So this makes perfect sense, okay? That if two events are independent, we don't have to write the probability of B given A. Probability of B given A is the probability of B, okay? So just remember that. I wrote it on the previous page, but I'm gonna write it again here. The probability of P given A is equal to the probability of B when the events are independent. So it makes sense that we would write this like this. Okay. Now the multiplication also makes sense, okay? We're multiplying because of the fundamental counting principle. That's where the multiplication comes from. Fundamental counting principle is super important in probability. We're going to talk about it in the next lecture too. So if we have two events occurring, and for the first there are 52 possibilities, and for the second there are 51, then the total number of ways that those two events can occur is 51 times 52. That's your bottom. That's your total outcomes. Now the desired outcomes, think of choosing the king and then choosing the queen. for every 4 possible ways that we could choose a king. So whether we get a king of hearts, diamonds, spades, or clubs, okay? For each one of those, there are 4 possibilities for our queen. So it would be 4 times 4, okay? So that would be our numerators. Let's take something where we can actually think about it with less numbers, okay? Let's go back to a bag with 3 red pieces of paper and 5 green pieces of paper. And let's make it 2 green, because then we can actually create. Okay. So in this case, I just want to make sure that I do this correctly for you. So if we have a bag with 3 red pieces of paper and 2 green pieces of paper, then we have a total of 6 pieces. I'm going to erase this. Let's go back to let's go back to the deck of cards, okay? So we pull out 2 cards. The first thing that we need is total outcomes. So we want the probability of a king and a queen. Okay. Now the probability of a king and a queen, the way that we would do this is we would say the probability of getting a king is 4 out of 52. And then we're going to multiply by 3 out of 51. So let's talk about why this is, okay? So in the bottom, total outcomes. So for every possibility, for every possible first card, and there are 52 of them, there are 51 possibilities for the second card. This is better than the piece of paper example that I was going to use because all of the cards are different. That's why I decided to stick with this. Okay. So for every one of the 52 cards, there are 51 possibilities that go along with it. Think back to our tree diagrams, okay? We have 52 possibilities in our first column, in our first level, and then for each of those, there are 51 possibilities that come out of it. And the reason why there are 51 is because let's say that we get an ace of diamonds on the first. Well, we could get any one of the remaining 51 cards for the second pull. If we get a king of clubs on the first, well, we have 51 possibilities for the second card. And this is true for every single card in the deck. Okay, so for every possible first card, there are going to be 51 branches that come out of it. That's where we get the 52 times 51 from. There are 52 groups of 51 cards. Now the same is true for the desired outcomes. Okay, we have 4 kings. So this could be like it's a separate tree. We have the King of Diamonds, the King of Hearts, the King of Spades, and the King of Clubs. I said 3 out of 51. This should be 4 out of 51. There are 4 queens in the deck. Okay. Now, if we had pulled out a king and a king, then we would have had 4 out of 52 times 4 out of 51. So I'll put that in here also, just so that you could see the difference since I put it incorrectly originally. 4 out of 52, and now this is going to be times 3 out of 51. Okay. Now for each of these, there are going to be 4 things that come out of it. There's going to be the Queen of Diamonds, the Queen of Spades, or the Queen of Hearts, Queen of Spades. Order doesn't matter though. And the Queen of Clubs. And there are 4 coming out of each of these. All the same. So there are 4 groups of 4. 4 groups of 4. We multiply. For every possible king, we have 4 possible queens that could go along with it. We could get a King of Diamonds and a Queen of Diamonds, a King of Diamonds and a Queen of Hearts, and so forth. We could get a King of Spades and a Queen of Spades. We could get a King of Hearts and a Queen of Hearts. So that's where this comes from. It's the fundamental counting principle. So we talk about the king and the queen, but then we talk about the total outcomes, and the total outcomes would be 52 and 51. Okay, so this is how we can determine a probability of 2 events happening together. Okay, and if they're independent, then it's just the probability of A times the probability of B. If they're dependent, then it's the probability of the king and then the probability of a queen given a king. And the probability of king given of a queen given a king is 4 out of 51. Okay, these are independent. These particular events are dependent. Okay. So let's take a bunch of different things. Let's take choosing a meal. Okay. Let's say that we have 3 appetizers. Six entrees and 5 desserts. These are independent events. We call them independent events because whichever appetizer we choose, it doesn't change the entree that we choose. So, for example, if we're asking ourselves, what is the probability that we choose soup and fish and ice cream? This is equal to the probability of choosing soup times the probability of choosing fish times the probability of choosing ice cream. And we don't have to worry about givens here because these are independent events. So the probability of the soup is 1 out of 3. Soup is an appetizer. Probability of the fish is 1 out of 6. Fish is an entree. And the probability of ice cream is 1 out of 5. Ice cream is a dessert. So this would be 1 out of 90. So what it's telling us is there are 90 possibilities, right? Number of possible meals is 3 times 6 times 5. That's 90. And then the probability of choosing this particular combination, well, there's only one way to choose that. So it's 1 out of 90. So it makes sense, okay? If we created a tree diagram, this makes sense that this is one path on that tree diagram, one branch, one set of branches that we follow. Let's say, for example, that we toss a coin and roll a die. And we want to know what is the probability of getting a head and a 6. Well, first of all, these are independent events, so we don't have to worry about the givens. So this is the probability of getting a head times the probability of getting a 6. Probability of getting a head is 1/2. Probability of getting a 6 is just 1 out of 6. And again, if we created a tree diagram like we did in the last lecture, we would have a head and a tail, and then from each of those branches, we would have 6 branches coming out, 1, 2, 3, 4, 5, 6. So there would be a total of 12 outcomes, and only one of them gives us a head and a 6, okay? Let's take some others. Let's say that the probability that a rotator cuff surgery is successful is 0.9. Okay, these are independent events. The one surgery being successful is not dependent on the next surgery being successful. So let's say that we ask, what's the probability that we have 3 successful surgeries? Well, the probability that the first being successful is 0.9. The probability that the second is successful is 0.9 again. They're independent of each other. And the probability that the last is successful is 0.9 again. So if we just multiply these, 0.9 times 0.9 times 0.9 gives us 0.729. The probability of 3 successful surgeries is 0.729. Let's look at the probability that none are successful. So the probability of an unsuccessful surgery is 0.1. If one surgery is successful, then a surgery being unsuccessful is 1 minus 0.9. So let's just write that in there. This 0.1 comes from 1 minus 0.9. This is an unsuccessful surgery. Remember, it's the complement. So if we want the complement, we just do 1 minus. So we do 0.1 times 0.1 times 0.1. Now, we know that this is going to be a pretty low number because the probability of a surgery being successful is 0.9. So to have 3 unsuccessful surgeries has got to be pretty low. And it is. Okay, and they're independent events, so it's kind of telling you, okay, well, if I have 2 unsuccessful surgeries, well, the third one is very likely to be successful because the probability of the 3 being unsuccessful is so low. Okay, let's say the probability of at least 1 being successful. At least 1 is successful is the complement, it's the opposite of all of them being unsuccessful. And this can be easier to calculate. I'm going to put in a 3. Right? Because if at least 1 of them is successful, then we're saying, well, either 1, 2, or 3 are successful. The only thing that doesn't include is if all of them are unsuccessful. So the easiest way to calculate this is by doing the complement of none being successful. So this is at least 1 of 3. This is the complement of none are successful. Meaning it's 1 minus 0.001. And if we calculate that, we get 0.999, which is really high. Okay, we're saying if there are 3 surgeries that are happening, they're all rotator cuff surgeries, then the probability that at least 1 is successful is almost certain. That's almost definite. It's not definite, but it's almost definite. It's really, really high. Okay, so that's something to know. Okay, let's take just a couple more examples. Let's say in a jury selection, so most of you have probably been on jury duty, but if you haven't, you basically go into a room and you have like 100 people there or something, and they choose a bunch for each case, and they ask you questions, and that's called a voir dire. And then from those people, they choose 12 jurors or 6 jurors, however many they need. So let's say that this is the big room with 100 people, and we say 65% of them are female. And 25% work in health. The 25% who work in the health field, I'm going to add in females here. So if we want to know the probability of somebody being female and being in the health field, we can say that this is the probability of someone being female times the probability of somebody working in the health field given the fact that they're female. Well, 0.65 or 65% are female, and 0.25 work in health if they're female. So we just go to our nice little calculator. 0.65 times 0.25 is equal to 0.1625. And we won't round that, we'll just leave it. Okay. Let's take the probability of female and not health. Well, this is the probability of female times the probability of not being in the health field, given the fact that they're female. And we know that 25% are in health. That means that there are 75% who are not in health. So again, we can just go to our calculator. And this is almost 50%. Okay, there's almost a 50% chance that they're going to be female but not in health. Okay. Let's move on. Okay. So the last type of events that we have when we're talking about two events are mutually exclusive events. So these are two events that have no outcomes in common. They can occur at the same time. Some examples. Rolling a 3 on a die. And rolling a 4 on a die. These are mutually exclusive. They cannot both happen. Either you get a 3 or 4. You can't get both. Okay. Just by contrast, rolling a 3 on a die and rolling an odd number, these are not mutually exclusive. Okay, they both can occur at the same time. So 3 is odd. Rolling an even number and rolling an odd number, those would be mutually exclusive. Both can't happen. Okay? Some other examples of not mutually exclusive, which is easier to come up with, would be somebody being a criminal justice major and over 25. So these are not mutually exclusive. Okay, you can definitely have criminal justice majors who are older than 25. Okay. So let's talk about how to calculate probabilities. So mutually exclusive, we're talking about addition instead of multiplication. Okay, for independent, when we were talking about those two events occurring together, we were talking about multiplying probabilities. Here we're talking about adding probabilities. So if the events are mutually exclusive, then the probability of A or B would just be the probability of A plus the probability of B. Okay, they have nothing in common. If they're not mutually exclusive, then the probability of A or B is going to be the probability of A plus the probability of B, but the difference is that they're going to have some things in common. So we have to take out those things in common so that they don't get counted twice. Okay? So, for example, let's take the probability of getting a 4 or an ace. So we're choosing a card. Probability of getting a 4 is 4 out of 52. Now remember, these events are not happening together. It's one event or the other event. So there are 4 aces and 4 fours and 52 cards, and there are 4 aces and 52 cards. There are no cards that are both 4s and aces. These are mutually exclusive. So it's just 8 out of 52. Okay, these are mutually exclusive. Meaning no cards are both a 4 and an ace. Let's take an example of events that are not mutually exclusive. So the probability. So here we're going to roll a die. Okay. So the probability of getting less than 3 or an odd number. So here, there's a 2 out of 6 chance that you get less than 3. A 1 or 2. There's a 3 out of 6 chance that you get an odd number. But there's one case where you get both a 3 and odd. Which means there are 4 numbers that are less than 3 or odd, and 6 in total. Okay, so let's just go through this. So these are not mutually exclusive, meaning you can get a 3 and an odd number. So this is the probability of getting a 3. So you could get a 1 or a 2. When I say the probability of getting a 3, I mean the probability of getting less than 3. This is the probability of getting an odd number. This is, you can get a 1 or a 3 or a 5. This is the probability of getting less than 3 and odd. So it's the probability of getting a 3, okay? Now notice, sorry, this is the probability of getting a 1. 1 is the number that's less than 3 and odd. Okay, so notice 1 is being counted twice here. It's being counted in this probability, but it's also being counted in this one, and we only want to count it once. So there are really what did I do? There are really only 4 possibilities. There's a 1 or a 2 or a 3 or a 5. That's where the 4 out of 6 comes from. You can get a 1 or a 2 or a 3 or a 5. We don't want to count the 1 twice, okay? This prevents us from counting this 1 twice. That's why we're subtracting, so that we only count that outcome once. It's being counted in this probability as less than 3, and it's being counted in this probability as odd, okay? Let's say probability of an even number. Let's go back to black. We're almost done here. Probability of an even number or a number greater than 4. So this is the probability of even plus the probability of a number greater than 4 minus the probability of both. So the probability of an even number is 3 out of 6. Probability of a number greater than 4 is 2 out of 6. Let's say greater than or equal to 4. Just so that we have something different than what we had before. Which means that this is going to be 3 out of 6. And then the probability of both, well, there's 2 even numbers that are greater than or equal to 4. So 3 plus 2 minus 2 is 3 out of 6. So let's break this down. What are the even numbers? The even numbers are 2, 4, or 6. it up so that you can see it. Hang on. Okay, so I'm just going to put this up higher. A 2 or 4 or 6. This one, the probability of a number greater than or equal to 4. Well, this is a 4 or 5 or 6. And this one, a probability of even and greater than or equal to 4. Well, a 4 or a 6. So what you can see here is that we have a 2, 4, or 6 coming from even numbers. Then we have a 4, 5, or 6 coming from numbers greater than or equal to 4. 2 of these outcomes have been repeated. So we're going to take out the repetition. That's what this one is. Okay? So we're taking out the 4 and we're taking out the 6. And that's what's happening here. Okay? Let's take another example. Let's take choosing a card again. Let's do one more with choosing a card. Okay. This is the last one like this. So the probability of getting a face card or a heart. So again, these are not mutually exclusive. If they were mutually exclusive, it would be simple. We're saying that there would not be any face cards that are hearts. So there are 12 out of 52 face cards. There are 13 out of 52 that are hearts. And then there are 3 out of 52 that are face cards and hearts. So we have the probability of a face plus the probability of a heart minus the probability of both. So this is 12 plus 13 or 25 minus 3. It's a 22 out of 52. And again, we like to simplify. Now we haven't been in the others, but we should be simplifying. Okay, so let's actually go back and do that because I want to make sure that you do that. Okay. So this 8 out of 52 is really 2 out of 13. It's divisible by 4. We're squeezing this in here. 4 out of 6 is really 2 out of 3. 3 out of 6 is 1/2. And then this 22 out of 52 is 11 out of 26. And then we'll do one more example of mutually exclusive. We'll do rolling a die again. And then we're going to do one with the table, and that'll be it. So rolling a die, and we're talking about the probability of 6 or odd. Okay, so this is mutually exclusive because there are no odd numbers that are 6. 6 is even. So this is the probability of 6 plus the probability of odd. There's 1 6. There are 3 odd numbers. So this is just 4 out of 6. And again, to reduce, it's 2 out of 3. And again, this is just a 6. This is 1 or 3. or 5. Mutually exclusive events. Okay, so let's move on and look at a chart. And what we're going to do is we're going to look at a chart of blood types. So blood types, there are 4 blood types. You could either have type O, you could have type A, type B, type AB. But then you also have an RH factor. So you can be positive. So like you could have a blood type that's O positive or O negative. You can have A positive or A negative. Okay? And we're also going to put totals in here just like we did before with the other chart. So these are like your empirical probabilities where you're asking people or you're taking the data. So let's say that there are 156 people who are O positive, 28 who are O negative, which means that there are 184 people who have type O, 139 who are A positive, 25 who are A negative, and 164 who have type A. 37 who are B positive, 8 who are B negative, and 45 who have type B, 12 who are AB positive, 4 who are AB negative, 16 who have type AB. There are 344 who have a positive RH factor, 65 who have a negative RH factor, and there are 409 people who we asked. Okay, so let's take the probability of type O or type A. So these are mutually exclusive, meaning you can't have type O and A. Okay, right? There's no column or row for that. There's no box for type O or type A and type A. So this is just the probability. I'm not going to put in the word type just to save some writing. Now the probability of O, we're not indicating positive or negative. So there are 184 people who have type O, 409 in total. And then for type A, there are 164 people, 409 in total. So we can add that. 184 plus 164. And that gives us 348. Now, I would like you to reduce if you can. I don't think you can here. Okay. Let's take instead the probability of B or an RH factor that's negative. Now this is not mutually exclusive because we do have type B that's also negative. Okay, so this would be a B negative. So this is the probability of a B plus the probability of a negative, and then minus the probability of a B negative. So the probability of a B, well, there are 45 B's. There are 409 people in total. There are 65 people who are negative, and 409 in total. And then then there are 8 people who are B negative. So those 8 people were counted both in the negative number and in the B number. So that's why we're subtracting it. We subtract it once because we only want to count them once. So this gives us 110 minus 8, or 102 over 409. Let's do the probability of O, or RH positive. So again, these are not mutually exclusive because there are O positives here. So it's the probability of O plus the probability of a positive minus the probability of an O positive. So the probability of an O is 184 over 409. The probability of a positive, we look at the positives, and there are 344 over 409. And then the probability of an O positive, we go to this box over here. These are the O positives. And we have the same denominator, so we just work with the numerators. 184 plus 344, and then minus the 156 people that were counted in both. And we get 372 over 409. Again, if you can reduce, try reducing. Okay. And let's do one more. The probability of an A or a negative. So this is the probability of an A plus probability of a negative minus probability of an A negative. There is a box for A negative. So the probability of an A is 164 over 409. We're going to the total number of A's, which is 164. Probability of a negative, total number of negatives is 65. And then the box that's A negative is 25. And we can go and we can calculate this. 164 plus 45 minus 25. And we get 184. And this would be mutually exclusive events. So these are how you would calculate it if you're given, essentially this is a frequency distribution. Okay, and that's it for 2 events.